Okay, hello students. Today is May 26th, and we're going to continue with chapter 2 this afternoon, okay? I'm going to review some basic relations about conservation of mass. You have to have in mind that there are certain principles which have to be satisfied without basically any restrictions. One of those is conservation of mass. The other usually is conservation of momentum, okay? Then we have to be careful because we have to worry about, even though if we include or not viscosity, but conservation of mass, conservation of momentum are general, okay? I would like to see at the end of the class if there is any problem with the assignment that you are very close to complete. And also, I would like to see how you people are doing with the extra assignment that I asked you to complete about Excel. Okay, so that's the agenda for today. Let's see if we can find. You see my screen? Anybody?
Yes,
Screen or half screen? Screen. How can I? Shoot. Swap. How about now? Full?
Yes, full screen.
Okay, now. So these are the topics that we will be covering, reviewing in this chapter. Okay. Conservation of mass, as I said before, nobody can avoid this principle. Everybody has to satisfy conservation of mass. Then, in this case, in subchapter 2.2, we're going to do a huge assumption. And that's that we have this, when we say irrotational flow, we mean no viscosity. Okay, so no viscosity allows us to do some sort of experimental observation, I would call it. Okay, and through that observation, the scientific people community thought that this irrotational can be satisfied when we have no influence from viscosity. So Laplace's equation that we are going to derive in this subchapter 2.2 is specifically valid for cases where viscosity is non-important, okay? Then we keep with irrotational flow and we deduce Bernoulli's equation, okay? In this case, Bernoulli's equation, you remember from your high school years, okay? Or even in here at the university, usually in physics, I don't know, 1 or 2, you work with Bernoulli's equation, okay? But the great news is that in this case, we're going to consider unsteady problems, okay? So here, we say viscosity is not valid. Here, okay, we said we have time dependence. Okay, and when we have time dependence, it's a big step because remember, this is ship dynamics class. So in ship dynamics, of course, we have something which depends on time. So we're going to use Bernoulli's equation with no viscosity, but including time dependence, okay? And because of this time dependence, we're gonna have a term which is called added mass, okay? So we're gonna have the integration of the pressure, and the integration of the pressure will give us a hydrodynamic force, and that's going to be basically equal to minus the added mass times the acceleration. Okay, so this is something which is very interesting. And then we're going to use this concept when we analyze the motion of a ship. And finally, in this chapter, since of course you know that in ship dynamics, the waves are the source of the excitation for the ship. Okay, we're going to study the main characteristics, principal characteristics of gravitational waves. Okay, for example, we're gonna say what's zeta zero, that's the amplitude, what's the wavelength, what's the k, that's the wave number, omega, if we go to the right or to the left, and things like that. See all of this in this last chapter. Okay, so you have a general idea of what we're going to be doing during this chapter. Okay, so today we're going to start with conservation of mass. Okay, so we're going to need that you recall from vector calculus, okay, the theorem, with some people call it Green's theorem or divergence theorem or Gauss theorem. It's basically the same. Okay, so I'm going to write in here. This is from a math book. It says that given a surface S, like here, see, I have a surface here, which is limiting this volume, okay? With normal unit vector, okay? This is common notation. See, this little hat, okay, means that this is a unit vector. Okay, so the amplitude of M is 1. Volume V. To avoid cases we can get some confusion, so to avoid if this is V or what, I put it something like this. So that means that this is big V. So this is capital V. So that's the volume, okay? So we have to be careful because the velocity could be something like this. We have, this is V, probably is the inverse of the density, and we have the volume like that. So if we have any doubt, what we can do is we can recall that this is vector, the velocity is a vector. So we have to be careful with these three. So when you write, try to be clear if you mean velocity, specific volume, or volume, okay? So, in a volume V limited by the surface S. Then, for any vector function, so let's call it, this is the vector function, and it can depends on X, Y, and Z. Okay, so that means that inside the volume, so let's draw here a reference system, okay? We have X, Y, and Z. So in every position, okay, we have a vector, and this is vector A. So in every point, we have different values for A, but A is a vector. That means that it has 3 components in the 3 directions that we have just mentioned. Okay, this vector is, this function, vector function is, it's a good function. That means it's differentiable. So you can calculate the derivative at any point. And also has unique value. This is classical, okay? Then the following relationship holds. Okay, so if we integrate over a whole surface, which is limiting V, we say ds a. This is dot product of n. So remember, the dot product of these two vectors produces a scalar, okay? And this is equal to minus the integration of the whole volume of dv, and then we have nabla dot a. So this is a divergence of a. Okay, now please, I forgot here, I'm an adjective of n. Let me change color to insist on that, because many authors, they don't have uniformity, okay? So this normal vector, okay, in this case is inward, okay? That means that you see, as you can see in this figure, is pointing toward inside the volume, okay? And this fact that we are defining this n inward, this influences the appearance of this negative sign, okay? So what I'm saying is that it is possible that in some books, you can consider this n pointing outward. And in that case, this sign turns into positive sign, okay? So we have to be careful. Now, in this case, inside the volume, of course, we are going to have our fluid, okay? That means that outside, see, this area, which is outside the domain where the volume, where the fluid is included, this could be the body. And of course, the body is the ship eventually, okay? Now, so we have to be careful with that, because in this case, if we multiply the pressure times n in time ds, we're going to have a force, as you can see here, which is pointing towards the fluid, okay? We have to be careful, because in this class, of course, we are interested not in the motion of the fluid, but in the motion of the ship, which is up here. So we have to be careful, because when we calculate force, we need to calculate the force applied on the ship. Okay, so it's the direction of the force that we need is the opposite of this one. Okay, so we have to be careful with that, because in some cases we use one or the other convention. Okay, so this is that. So this is an scalar, okay, because this is dot product, okay, and this is also a dot product, okay. So just to remember that this operator, we call it nabla operator, is by definition the partial derivative in x direction plus the partial in y direction plus the partial in z direction. Okay, so we can apply this to a scalar. And if we apply to a scalar, we will going to have a vector. Okay, if we apply this operator on a vector, okay, we have two options. We can apply it using the dot product or the cross product. If we use the dot product, the result is going to be a scalar. And if we apply this operator, nabla, on a vector through the cross product, the result is also going to be a vector. Okay, so please, when you write this, especially in the exams, okay, try to be clear so we can avoid discussions, okay? Please, if there is any question, try to raise your hand or something like that, and we will try to clarify as good as we can. We can go on. Now, there are a couple of useful relationships from vector that we're going to need, and this is what we're going to recall now. The first one is...
Doctor, there is a question from Daniela side.
Okay, go on.
Doctor, I have a question about the...
Cannot hear you. Would you please get closer to your microphone, please?
You can hear me now?
Yeah, I can hear you now.
Okay. I have a question about the n vector. You say something about the direction, but I'm not clear about that. The direction of the n vector is always inward, or
no?
Or...
That depends on the application, depends on the situation, depends on the authors. Okay. For example, here I have the fluid. Okay. If I were a mathematician, I'm interested in here, what happens inside here, the domain, right? Because in here is this where we're going to have this A and all of that. If I'm a naval engineer, I'm going to draw here, this is a ship, obviously, right? And here I have the fluid. So I have gamma and whatever, right? Density and all of that. So in this case, this is the volume and this is the surface. So the surface will be something like this. It goes like that. Closes somewhere in the infinite. This is the Pacific Ocean. Now, in this case, this n, in this case, and this is this n here in the expression for the integral, this n is pointing like this. And this is the mathematician loves it, express something like this. But for us, okay, I would like, and let me change color. I would like to express this in a different way. Why? Because I'm not interested in the action on the fluid. I'm interested in the force on the body, the ship. Okay? So if I would express the same principle using this n, in that case, what I'm saying is that I have to be careful because in some books, you will see this and this sign, negative sign, will appear as positive sign. So what I'm saying is that you have to be careful, okay? So in the statement of the theorem, you have to be careful in what sense, okay? The normal vector is being defined by the author. That's what I'm saying. We have to be very careful. Misayo?
Okay, doctor, thank you.
Okay, no problem. So the problem is that my understanding is that hydrodynamicists, they are people who are very close to mathematics, right? As a matter of fact, in the 70s, there was a very, very renowned hydrodynamicist in Michigan. I don't remember his name, but he was so good that MIT robbed him from Michigan. So they offered a good contract and they took it to Michigan, to MIT, because he was so good. And the thing is that originally, this professor was a mathematician, right? So that's the problem. So yeah, okay, if you are interested in studying the fluid, of course, the n, you would like to point it to the fluid. But as with us, we are engineers, we like to see the influence from the fluid on the ship, on the body. In that case, I would use the n pointing to the body, because in that direction will generate a force. So if we want to use the mathematicians, let's say the mathematicians' way of calling this n, okay, which is this one here, in this case, what we need is, since we want to work in this direction, what we need is a negative sign on the n. We'll see this in a minute, okay? So we have to be, the only thing that I'm saying is that we have to be very careful with the n, okay? So if we say it is pointing inward, the fluid, okay, so if we want to calculate the force, in that case, on the body, we're going to need a negative sign. If n points inside the body, that means outward from the fluid, then we don't need any sign, any sign on the end. That's all. Okay, so some useful relations from vector mechanics. So in this case, I just put it, this is dot product. Okay, this is dot product. Okay, this is the nabla operator, nabla, and in this case we are acting on a vector. So in this case, the result is going to be a dx plus the a dy, the a, I'm sorry, ax, xy, and the az. You see, this is an scalar. Okay, so that we're going to use this dot product quite often. What else? Continuing with this dot product, we can calculate the dot product of a vector, like in this case, a dot n. But in this case, n is a unit vector, okay? If n is a unit vector, in this case, a dot n will produce the component of a in the direction of n, okay? Maybe you remember this, right? So you have, this is a, and this is, that we make the product of the two, the amplitudes of the two, and multiply by the cosine between the angle, right? Remember, this is classical from, and what we're doing is simply this. So a dot n, remember, when we use this, that means that it's a unit vector, is the component of a in the direction of n. Okay? And this is typical now. For example, let's suppose that we have like a surface, little surface here. Okay? And let's suppose that we have this little force here. There is some pressure pulling out from here, and this is the result. This is a vector in this direction. Now, and let's suppose that we are interested, for example, in the vertical direction. See, for example, let's suppose that we need the vertical component of dF. For example, we say summation of forces in the vertical direction is equal to mass times the vertical acceleration. We're going to say that in chapter 3. In this case, what we can do is, okay, we can say dF, and we have to do is multiply by a unit vector in the z direction. Do you remember the unit vector in the z direction, people? The unit vector in the z direction, Miss Hidrobo, do you remember what was the name of the unit vector in the z direction? Unit vector in the z direction. No, Mr. Zamora, do you remember how do you call the unit vector in the z direction, people? Come on.
The K?
Okay.
Yes, K. So it's just K. So this is going to be, in this case, for example, this is going to be, let's call this N. Okay. So N gives the direction to F. So we're going to have, this is N1, dfx. This is in the x direction, so this is I. plus N2 dfy, this is in the direction J, and plus N3 dfz in the direction K. And this, we make it dot product with K. And in this case, according to our explanation, what we are going to obtain is the component in the Z direction. And this is what we're going to obtain. Okay, so it's going to be, see, you do the dot product of this times J or times I, since they are orthogonal, the dot product is going to be 0. So the only thing that we're going to obtain is N3 dfz. No, that's not correct. In the 3 cases, that is incorrect. Let me correct it. Let me correct this. They don't have subindices. The amplitude is the same. I'm sorry. Yeah. So it's going to be N3 df. Okay, indirectly, that's what we're looking for. Okay, that's the component EF in Z direction. We're going to use this expression in the next session. So this df, the amplitude of df, we can say that since this is this were an elementary or a differential surface, this df could be set as ds, the area, times the pressure. So the component in the vertical direction, we can write it as N3 P ds. And then we can proceed to integrate. But in this case, remember that we are taking the component of the force in the direction of the normal. In this case, this is the direction that I'm considering. Okay, so we're going to apply this concept that the dot product of a vector with a unit normal vector will give us the component of this function in the direction of the normal. So we're going to use that in order to calculate the mass flow, which is crossing a certain element. Okay, so suppose that we have this is an elementary area, very small. So we can say that in this area, since it is very small, we can say that the velocity is the same in any point on this little element, since it is very, very small. Okay. Now, in this case, let's suppose that we have this vector velocity v, right? In this case, we're going to say, okay, this is the normal unit vector. Okay, so we can say that v dot n will give us what? Will be the component, the velocity in the direction of n. In this case, okay, since this is a normal, we may call it sub n. So v sub n is the normal component, normal to the surface of v in the direction of n. So that's that. Now, since we have this component, so it's having something like this. This is V sub n. And we're assuming that this is very small. So this Vn is the same in this small element. So we can say that if we multiply this Vn times this little area, will give us the flow. So the flow, or volume flow, through ds, So it's going to be something like this. Like this is going to be Vn ds, because this is the normal component. For example, in case Vn is tangent, I'm sorry, no. In case V is tangent, please do not write here because get me confused, okay? There's somebody who is bugging me. Okay, in case V is tangent to the surface, okay? For example, let's suppose that I have a surface here, okay? And let's suppose that we have this is the velocity, okay? In this case, this is n. From here to here is a little surface called ds, okay? So in this case, in case V is tangent to surface, then n is perpendicular V. And in that case, V dot n is equal to what, people? If n is perpendicular to V, what is V dot n? Anybody?
0.
0, yes, 0. And you can see it here, right? If you go like this, tangential, you don't cross the surface, okay? And this is what we're saying here. Is Vn is 0, like in this case, there's not going to be any flow through the S, because in that case, the flow is just tangential, okay? Now, finally, we could, this is a volume of flow. We can multiply this by the density and we can guess mass flow. Remember, what is preserved is the mass, not the volume. So if we need to apply principle of conservation of mass, we need to go to mass flow. So if density is rho, then mass flow through ds is rho V dot n ds. Okay, so this is a differential rate of mass through ds. Let me go back a little bit. You see, I have a V dot n here, and at the beginning, when we established, I have B dot n here. I have A dot n here, right? So we can say that we could try to apply here, to this term, Green's theorem, okay? So because I have something, V is a differentiable unique value function. So it could be replaced instead of A, and we could go on and apply Gauss Theorem. Okay, now we have to insist, let me change color just to be clear. If N points inward. Then this flow of mass enters the volume, right? So it's like having, okay, inside here, see, inside here, this is V inside, and outside is out here. Okay, so in this case, N, you can see it here, is pointing inward. So V dot N, that means the component of V, normal to the surface, but pointing inward to the surface. That means that when we go multiply that by ds, that's the flow through ds, which is entering the volume. And of course, we multiply by rho, that's going to be the flow of mass, which enters the volume V. Okay? That's that. Now, we have to go now to ask this. If we have some mass going inside the domain, okay, then what? Okay, so it's having like this. I have it, this is S, okay, and I have some, this is V. So I have this component, this is Vn, pointing inward, okay? So all of this means that in this little region, there is some mass coming inside the volume V, okay? So if we integrate our expression all along the S, that will give us the total mass of flow coming into the domain. Now, the problem is that here you can think that this is composed by little volumes, and each one of these has a density. Okay, so we can say that to avoid any loss or appearance this flow is going to produce a rate of change of the mass contained okay, so this is going inside. So this at the end is going to produce a change in the mass contained in V. Now, what's the mass contained in V? Well, the mass is going to be the integral over the whole volume of the mass of each one of these little volumes. So it's going to be the density times dV. So if we have a mass, a flow of mass coming inside the volume, at the end, this mass here, this integration, will have to produce a different value because the mass is coming inside. So it has to produce an increment in mass. Okay? Put it here. So the rate of change is going to be dm dt. It's going to be the derivative with respect to time of the integral of rho dv. So what we're saying is that if we integrate this mass flow through this little ds around all the surface S, okay, that mass which is coming inside will have to produce a rate of change of the mass contained inside the volume. Now, what happens in the steady case? In the steady case, dm dt is 0, right? Because there's no change with respect to time. In the steady case, dm dt has to be equal to 0. So the integral of the whole surface of, I'm going back here, rho v n ds, in that case, so rho v dot n ds has to be 0. Because that means that if we have coming fluid coming inside, there must be another part of the surface where the fluid is going out, right? Because the mass, the total mass contained in the volume V cannot change in time, because we're saying that the problem is steady. Okay? So to have conservation of mass, as we have said here, the two of these quantities have to be equal. So we can say that in general, the integration of rho v dot n ds, this is the total flow through the surface which is coming inside the volume. And that's going to produce a rate of change of the mass contained in the system. So that's conservation of mass, right? So if we're considering an steady case like this one here, in this case, this term on the right-hand side is 0. So this integration has to be 0. That means that, for example, let's suppose that we have a reservoir here, and we're pouring some water inside, okay? So this is our volume V. So we have flow through S. This is S. So we have, this amount is going to be positive, right? That means that the mass, which is inside here, is going to increase in time. Unless we have another pipe, and if this is equal to that, okay, in this case, this mass is conserved. So the rate of change of this integral is going to be equal to 0. Okay. Now here we have an integration of a vector function. So we can see, or we can consider that this is a vector. Okay. So this is a vector function which is differentiable. I mean, you can calculate the derivative of this. It has a unique value in every point, so there is no problem. So we can apply Gauss theorem. Let's go back and let's review what was Gauss theorem here. So we are saying is that instead of A, we're going to put rho V. So that's going to be equal to minus dV nabla dot rho V. Let's do it. Okay, so instead of the integral on the left-hand side, which is the integration on the surface, this is integration on the surface, this is integration on the volume, Gauss theorem says that is equal to minus the integration on the volume of what? Nabla dot the function, with the vector function, which is rho v times dv. And that's going to be equal to d of dt there. Okay, so both are integrals over the whole volume, so we can put on one side and we can say that the integral over the whole volume of the derivative of rho with respect to t plus this term here, nabla dot rho v dV is equal to 0. So this is an integral expression for conservation of mass. Okay. If you remember this derivation, we have not said anything about viscosity. Okay, so this has to be accomplished no matter what. It has to be satisfied. Okay. Now, what happens, for example, if we have this volume here, and we want to consider a certain volume? For example, let's see if we, okay, I want to consider my volume like this. Only this is my volume. We have to satisfy this? Yes. Now, I want to consider another volume, just this part here. We have to satisfy mass conservation? Yes. So this has to be satisfied no matter what's the shape of your volume. So this is V1, this is V2, this is V3, whatever. But always this has to be satisfied. So what's the only way we can do that? Well, you can remember from our math classes. So we can say that since V can be any volume, then the only way we can be certain that this is going to be satisfied is the derivative with respect to time plus nabla dot rho v is equal to 0. Okay, so this, we call it an integral form, and this is called a differential form. This is integral, this is differential, and both has to be, well, you can choose which one to satisfy. In certain cases, we're going to do an example. Remember the conservation of mass in a pipe. It's going to be 0. And in other cases, we have to consider this other on the right-hand side, the differential. But both has to be satisfied. Is there any question, people? Okay, we're going to take a break, a 5-minute break here. Okay, so Isaac, you can stop recording. 5-minute break. So it's 4:58. So we reconvene at 5:03.